Well, why don't we make a start? Good afternoon, everyone, and thank you for joining this afternoon's research showcase looking at how we can deliver a greener future for aviation. My name is Richard Oldfield, and I'm the Chief Exec of the National Composites Centre, which is part of the High Value Manufacturing Catapult and a subsidiary of the University of Bristol. And I'm very pleased to be chairing this afternoon's session, having spent 25 years in the aerospace industry before joining the NCC. I'd just like to share a couple of slides with you by way of introduction. I think everybody will be well aware of the environmental challenges that are facing the aerospace sector. And despite, we'll go to the next slide, please, Emma. And despite the current dip caused by COVID, emissions from flying are forecast to continue to rise steadily, as you can see on the graph on the right-hand side, as the demand for increased air travel continues to grow, especially in Asia and the emerging regions of the world. And if we're to achieve a net and ultimately absolute zero emissions from flying, a complete transformation of the industry will be required. This can be described as a wicked system-level problem involving not only improved aircraft, propulsion and fuel technologies, but also changes in the way aircraft are operated and the policy and behavioural changes that are required to deliver the reduction that is required. Next slide, please. The UK is already taking a leading role in this transformation. It's established the Jet Zero Council, supported by the Prime Minister and chaired by Emma Gilthorpe, who's the Chief Operating Officer of Heathrow, and includes key industry and government representatives. Developing a net zero roadmap for aviation. You can see a draft copy of that on the right-hand side of this chart, and that will be published in the coming weeks and months with various initiatives underpinning it. And supporting millions of pounds of research through UKRI, Innovate UK, and the Aerospace Technology Institute, to name but a few. And one of these programs that you will have seen launched recently is called Fly Zero, which is a specific study looking at the aircraft of the future. But we're not the only country committed to this. And you may well have seen recent announcements in France and America indicating a growing commitment for change. And the aim of today's showcase is to explore the work the University of Bristol is doing to support this effort. I'm delighted to hand over now to Professor Jonathan Cooper to lead the presentations. Jonathan is a Fellow of the Royal Aeronautical Society and the Royal Academy of Engineering and holds the Airbus George White Professor of Aerospace Engineering position at the university. He is also currently the President of the Royal Aeronautical Society. Jonathan.
Thank you very much, Richard. Good afternoon, everybody. I've got a couple of slides to show you. The first one here is a bit wordy, but the key take home is there are many technical challenges that need to be faced for us to enable greener aviation and eventually zero emissions. And there is no silver bullet. There is no one single technology that's going to transform things overnight. We can't simply just replace kerosene, and it's going to be almost impossible to retrofit current aircraft. So the likelihood is we're going to have a range of different solutions where we're going to be gaining 2%, 1%, 3% from different options and all of those together. One of the key things from that is that we are going to have to produce much faster design and particularly certification requirements and capabilities. And then I've just put together a whole series of different technologies, some of which are just what can we do with current technology, so better engine efficiency. So there's been some great developments there, but if we're not careful, we may do well with carbon, but generate more NOx and contrails. Biofuels are muted as quite a quick solution, but then you've got problems with the generation, and are you actually taking away food resources to be able to generate fuels? Flight operations is quite a simple one to improve air traffic management, perhaps to avoid contrail generation. Ground emissions, so the EU has a target for emission-free ground operations in the not too distant future. Are we going to move towards novel configurations? We've had the same aircraft, essentially a tube with wings and engines on pods for 50 odd years now. But there's many things like high aspect ratio wings, blended wing bodies that are being proposed. But how do we explore these designs? And again, how do we certify them in a fast and safe manner? Batteries, is an obvious choice, but the power density is not good. So okay for flying a small Uber type taxi around Bristol, say, but you're certainly not going to be able to fly to Australia using batteries, and you've got to generate the electricity as well. So perhaps you're moving the problem. You need to do that in a green manner, and perhaps have hybrid solutions, say like big ships do, where you, or cars, where you swap between electric and more conventional forms. We have hydrogen, which has got good energy density, but there are quite significant problems in applying that to aircraft. We need to consider the entire environmental effects. So from the manufacture of the aircraft through the operation and then through to disposal. So that's quite a problem with current composite designs. Aircraft or airport infrastructure needs to be part of the whole big equation. And then finally, of this list here, noise is very important, and not just around airports. So say perhaps we could increase the angle that aircraft land at, but there's a lot of move with things like future flight for urban air mobility. And, the noise is going to be a big environmental problem. So also needs to be considered. Okay, that's just a quick list. There are many more. The next slide is what is Bristol University doing about this. We have lots of really good world-leading research groups. And actually, if you look at these bubbles around on this plot, you see that we have an awful lot of capability in terms of green aircraft technology. So from the flight physics, which is the structures and the aerodynamics, through to the propulsion, data science, big data techniques, how do we simulate and validate and then test and certify. And again, those are going to be really important things for the new technologies. And then how do we do the design? So we could go through each of these one by one and probably spend a couple of hours discussing each of them. So I won't do that, but just to say that Bristol does have a wide range of expertise, and we're trying to work together to find ways to producing more complete solutions. Data science is probably going to be the key thing that ties everything together, particularly when you're getting to really big, complicated design issues. And then things like talking to our colleagues in the Faculty of Science in atmospheric chemistry, for instance. There's a lot of other things going on in the university that we need to exploit. As a final thing, it's not just aviation this applies to. You're not just want greener aviation, we want greener transport, we want greener infrastructure. So a lot of these technologies will map across, and there's good work going on and a lot more to do in the future at Bristol. So this afternoon we have 3 short talks by, well, I'll say experts, but I'm counting myself as one of those. So perhaps that's singing, not blowing my own trumpet. But anyhow, so we have Valeska, who's going to be talking about some of the work on the hydrogen storage. Mahdi will be talking about work on aeroacoustics. And then I'll be finishing off the short section of 5-minute talks by talking about some air elasticity and how that applies to producing environmentally friendly wing designs. Okay, Valeska, I'll pass on to you for your short presentation about powering greener aviation with hydrogen. Thank you.
Lee. Okay, thanks, Jonathan. So I'm just going to give you a very brief overview of one of those bubbles in Jonathan's diagram, using hydrogen for sustainable aviation. So if we can move to the next slide, please, Emma. I guess the first question is, why are we interested in hydrogen? And why do we, well, I personally think that hydrogen has a great future in terms of helping to get to net zero with aviation. And one of the benefits of hydrogen is it has a really high gravimetric energy density. In fact, it is the highest gravimetric energy density fuel that we have. So that means, so for example, kerosene has a fuel density in the region of about 40 megajoules per kilogram, for example. Batteries are about 1/40th of that, so less than 1 megajoule per kilogram. And hydrogen has about 3 times that energy density per kilogram. So it's a very light fuel, and it packs a lot of punch for the number of kilograms that you have to have on board. a vehicle. So that's one big bonus for hydrogen. The second one is that it can be generated from renewable sources, such as solar and wind power. And that means that its production can be made more equitable. People can generate hydrogen using just renewable electricity and pure water, so using electrolysis, for example. And so it has a potential to be a complete green cycle in terms of a sustainable fuel. And then finally, if you use hydrogen in either a combustion engine or with a fuel cell, then the only byproduct is the regeneration of water. So it has this potential to be a zero carbon fuel, and also that you haven't got the problems with NOx or other particulate emissions that you would have with other fuels. So then we come to the question of what are the advantages of hydrogen for aviation? Now, as you remember, it's a very high gravimetric density fuel, so it's very lightweight. And this is important when you think of how much of a plane's weight comes from the amount of fuel that needs to be carried, especially on transatlantic flights, for example. So in terms of aviation, the saving in terms of the weight is very important. A second aspect is that, as Jonathan and Richard alluded to, there are a plethora of different technologies that are available, battery electric or electric powered aircraft being one of them, but electric aircraft aren't suitable for long haul flights. So if you wanted to fly from the UK to Australia, for example, batteries don't have the energy density. You'd have the weight of the batteries alone would be prohibitive. And so for long haul flights, hydrogen is one of the most promising alternative fuel sources. The third advantage is that, as was described in the introduction, we're going to need a really drastic transformation of aviation if we're going to meet these zero emissions targets. It's not just a matter of making our existing aircraft more efficient. We need to look at ways where we can cut out the carbon, the particulates, and the other emissions from aircraft. And so, using drop-in fuel solutions like biofuels, for example, is just displacing the emissions and causing emissions at higher altitudes. We really need to go to something like a hydrogen plus fuel cell combination, so that we can eliminate the emissions from our aviation. So this is one of the ways that we can drastically reduce emissions to try and get to those net zero targets. So what are we doing in Bristol to address these issues? Well, in Bristol, we have some expertise in hydrogen storage. This is my area of interest, and it's looking at not only conventional storage of hydrogen in either in high pressure tanks or as liquid hydrogen, but also looking at novel material solutions using things like, we use nanoporous materials, which are also termed molecular sponges. And these are materials that can suck in and store hydrogen at really high densities. So looking at inventive ways to be able to store the hydrogen more efficiently and safely on board an aircraft is one area that we can help. Secondly, we also use some of these novel materials to help with the generation, the purification, and the stabilization of hydrogen. And this is really important if you're considering storing, say, liquid hydrogen over a 48-hour cycle or over a long haul flight. You want to prevent boil off, and some of these materials are very good at helping to retard the loss of hydrogen through boil off. In addition, if you use fuel cells, then you need a very pure hydrogen source. And so we're looking at some good solutions for that. And I'd be remiss if I didn't mention that Bristol has a world-leading Composites Institute. And we're also closely linked to the National Composites Centre, and this is going to be essential if we're going to have to redesign the body of the aircraft to accommodate these different fuel solutions. So composite design and manufacture to make lightweight designs of aircraft, and to and you have an additional flexibility when you're working with structural composites, and in being able to integrate the new fuel, the new power delivery within these aircraft. And so there are lots of opportunities in being able to embed functionality and new designs into the new generation of aircraft. So my last slide is just pointing out that there are a lot of people from the lecturer level to research fellows, postdocs, and PhD students in engineering who are working on different aspects of hydrogen for transportation and aviation. And we have links to the Hydrogen and Fuel Cell Research Hub, where we're funded by the EPSRC, but also have industry links. And we've also got colleagues in chemistry and physics who look at different aspects of hydrogen generation, hydrogen cogeneration, and all of this expertise can, and the broad base of knowledge, means that we can make some really good contributions to making hydrogen a possibility for sustainable aviation. That's all I wanted to say for my brief overview. Thanks, Jonathan.
Okay, over to you, Mahdi.
Thanks, Jonathan. So I'm going to talk about the aeroacoustic research activities at the University of Bristol. Again, going back to the chart that Jonathan showed, noise is one of major issues facing aviation, and moving from traditional aviation, if you like, to a new era of aviation, we have some new challenges, and that's what we're trying to do at Bristol. Next slide, please. So unlike my colleague, I've put a brief description of myself. So I was at Royal Academy of Engineering Research Fellow at Cambridge, and then back in 2013 moved to Bristol to form the aeroacoustic team at Bristol. And my research activities hover around aerodynamic noise, development of different flow noise control methods, duct acoustic, and also acoustic propagation effects. Next slide, please. So our group is pretty large. It's probably one of the largest group in Europe right now. We have 5 academics, lecturer, senior lecturer, and professor levels, over 20 PDRA and PhD students who are funded through different sources. We have several EPSRC, several H2020 and Clean Sky, as well as half a dozen of industrial projects at the moment. Over the past 5-6 years, we have attracted over 9 million with current 5 million active projects. And you can see the logo of some of our sponsors down there, with EPSRC and Horizon and Clean Sky being our main source of research and facility income. Next slide, please. So what we're doing at the University of Bristol, realizing the change, the drastic change that the aerospace sector is going through with future flight, urban air mobility, a lot of research at Bristol is going towards understanding the noise generation, especially for the new configurations. I've got some slides that I can show later, show you in the Q&A session, but with blended wing configuration, distributed propulsion configuration, all these things means that the noise signature of aircraft is going to change. And as a result, a lot of effort has been put into understanding these new noise sources. And based on our understanding of the noise generation mechanisms, we try to develop new and novel noise control methods. Some of these things can be purely noise control, like acoustic liners, but also on flow control using active and passive methods like serrations, flow injection to control the noise at source. Once we understood the noise generation mechanisms, we try to propagate the noise and understand the noise propagation over complex terrain, which is quite an important topic, especially in the area of urban air mobility or helicopter noise. Next slide, please. So Bristol is home to some major infrastructures at the moment, quite unique in the UK and Europe. We have the UOB aeroacoustic wind tunnel. You can see it on the left side, which is now a national wind tunnel facility. So this wind tunnel enables us to experimentally measure the noise from different aero components, whether it's a wing or propeller or the landing gear system, etc. The wind tunnel is equipped with lots of microphones and beamforming array and flow measurement devices like PIV, LDA, hot wire, which enables us to properly understand the noise generation mechanism. So this is a national wind tunnel facility, which shows the importance of that for the UK. In the middle, you see our UOB high-speed jet facility. So this is a jet noise facility for understanding noise from high-speed jets. This is, again, a major infrastructure, quite unique in the UK and involved in several industrial and EPSRC projects. We also have some other facilities, some of them quite new. You can see there on your left, the pressure neutral acoustic wind tunnel. This is designed for propeller research, again, realizing the shift in the research from jet to propeller. We have designed and built this new wind tunnel, which enables us to do proper research on propeller aerodynamics and noise. And then down there, you see the grazing flow impedance tube, which is, again, I think the only facility with such capabilities in the UK. And that is used for designing acoustic liners, which is quite an important topic for next generation of aircraft. Next slide, please. And this is my last slide, again, on the capabilities of Bristol. This is a wind tunnel that's currently being built. Again, a seriously major infrastructure investment. We call it boundary layer wind tunnel, and will be used for understanding boundary layer interaction and also development on technologies on low drag surfaces. Again, in line with the current activities on low drag and low emission aircraft. Back to you, Jonathan.
Thank you very much, Mahdi. I suppose the attention now goes to me. So I'm going to give a short overview of some of the work on using air elasticity to help design more fuel efficient and environmentally friendly aircraft. We don't have an air elasticity research group, but this is spread across 3 research groups, so composites, fluids, and also the dynamics and control, and involves, as I say, about 10 academic staff and about 15 researchers, mostly funded by the ATI, the EU, and also some from the EPSRC. So what is air elasticity? Air elasticity is the interaction of the aerodynamics with the structure. For students listening, you have spent, well, when we were allowed to, spent many happy hours in the Pugsley Lecture Theatre. Pugsley was one of the 2 people who actually came up with the term air elasticity, and that triangle in the top right was created by Roderick Collar, who was the founder of the Aerospace Engineering Department at Bristol. So we have a big history in terms of aeroelastics. If the wings bend and twist, that affects the aerodynamics, but that then affects the loads on the wing, which then bend and twist again. So we have this continuing interaction. Initially, it was found, and you have to design an aircraft because you can have catastrophic structural failure. So something called flutter. There's lots of fairly scary videos to see on the internet. But it also has a big effect on things like the response to gusts, the response to the aircraft on landing, and these resulting loads influence the aircraft design. The bigger the loads are, the heavier your structure has to be. Also, if your wings don't bend in the optimal shape, you'll have more drag and you won't be able to fly so far. So what the research that I'm involved with does is trying to exploit the structural flexibility while making sure that all of the nasty things don't happen. So we move to the next slide. I was going to put an equation in, but I thought, no, I can't possibly do that. So this is what all first year students know as the Bridget range equation. And essentially it says that if you want to fly further, you have to have better aerodynamics. So you have to have less drag, more lift. And also if you have engines which burn less fuel, that also increases your range. And also if you have less weight, that increases range. And a lot of what I've been trying to do is to try to combine these three things together, and rather than just saying, let's make the structure as light as possible, or let's improve the aerodynamics as much as possible, can we get a trade-off and use those interactions? So we move to the next slide, which is perhaps a little busy. We got the equation that we've all going to be tested on at the end of the talk, but how does the research help with that? So in the top left, we see two morphing structures. So that's saying, can I change the trailing edge, so the back end of the wing throughout the flight? So that's Ben Woods is a colleague of mine working on what's called the fishback. The orange structure there is a leading edge, and you can slowly change those shapes in flight to improve the aerodynamic efficiency. Quite a lot of work looking at novel configurations. I'll talk about what are called high aspect ratio wings, so longer wings, but also things like forward swept wings as well, which theoretically give you better performance, but we still don't know quite how they would appear in flight. Key also things that we're looking at is reducing the weight. So we can do that by using composites, but also if we increase the speed at which things like flutter can occur at, that is good because it means we can reduce the weight. Or if we can reduce the effect of gusts. So, you know, we fly and the captain says, put your seatbelt on. If we can reduce the effect of those gusts, not only will it be good for you as a passenger and you won't spill your coffee, but it means there's less loads on the plane. The bottom right-hand corner is showing some work we do with the Composites Institute. And that's by being able to use what's called toe steering. So the composite is laid like using an upside down sellotape dispenser. And by changing the shape of the composites, we can affect the global response. We can affect local behavior like buckling. And also we can improve the performance of the control surfaces. So it's a very complex, not just manufacturing, but a complex design problem. Finally, at the bottom, lots of work on optimization and particularly robust optimization. So how do we take into account the sensitivity of inaccuracies, but non-repeatability with our manufacturing and our design? And also distributed propulsion. We're not necessarily going to have 2 big engines or 4 big engines on aircraft. We're likely to have lots of very small electric or hydrogen powered propellers, and looking at that can have some quite dramatic effects on the design. So the next slide, please. And this is the final 2 slides are talking about high aspect ratios, and you can show that by increasing the span, so making the wings longer, you reduce what's called the induced drag, and that gives you better performance. But there's a lot of things that could be a disadvantage. So you may need extra weight to carry the load. The wings are highly flexible, which could cause problems. The roll, and we want to be able to control the aircraft. So there's certain roll limits that we need to do. Another key effect is that if your plane is too long, the wings are too long, you'll get charged more by the airports for the airport gate sizes. So that's why 737s and A320s are almost, you know, similar span, and that's because they're just below moving into the next gate category. And the design is much more complicated. The chart at the bottom is showing that how over the years the spans are still increasing up to about 11 or 12. But in terms of sort of calculations, not just from Bristol, but all over the world, we ought to be aiming for 19 or 20. That seems to be quite a sweet spot. So on the next slide, we move to that, we'll look at a capability of trying to enable high aspect ratio wings. So we look at the picture on the left-hand side. If the wing is held undefected in flight, we have a high aspect ratio, longer wing, therefore less induced drag. When we land and we taxi, we fold the wingtip up, and that enables us to fit into the gates without having to pay more money. If you've got some spare cash and want to buy a 777X, you can now buy one of these, although I don't think there are any are actually flying yet. But where we've made quite a breakthrough working for the last 7-8 years with Airbus is by enabling the wing tips to be able to float in flight. And by using these folding wingtips, so it's essentially like having a door hinge. So they're just held up by the aerodynamics. And when you get hit by a gust, they move up and down. I ought to move my hands so you can see them rather than waving around. So we can see here 3 pictures. So the top one is a rig in our 5x7 wind tunnel. So you can see the wing. The wind is off, so therefore the wing is drooping down due to gravity. When the tunnel flow starts up, that wingtip will then move up. The black wings across the wind tunnel can be moved and simulate turbulence in the tunnel. So we've shown that we can reduce the gust loads quite dramatically using this technology. The green and red structure there is looking at a rolling rig. So this spins around, and there are videos, or if people want to contact me, I can give you links of showing how the folding wingtips actually improve the roll performance. And then the final demonstrator was something we were partially involved with is the Albatross 1, which is an Airbus demonstrator. Again, you can see the folding wingtips on both sides of the wing. Those again are held up by the air, and again, if you look for Albatross 1 on the web, you'll find videos of this flying and reducing the load. So that's a great example of how we've taken the technology, developed it, and then worked closely with industry who are able to apply it, and hopefully move someday to actually applying this to real aircraft. Okay, so thank you for your attention for this part. Thank you to Valeska and to Mahdi for their short introductions about their research interests. And I'll now pass back to Richard, who's going to ask some questions or chair the rest of the session. Thank you.
Yeah, thank you, Jonathan, and thanks to the rest of the panel. We're now moving into the panel discussion part of the agenda. So I'd just like to encourage, some people have been brave and put questions in the Q&A. So please could I encourage others of you to do the same, and hopefully we can have a rich debate for the remainder of the session. But I'd just like to kick off before addressing the questions that are in the Q&A panel, to all of the panel, but possibly starting, Jonathan, with you first. Given that some of the technologies that we've just seen demonstrated and the range of issues that we need to address, what do you think are the most likely combination of social, economic and technological changes that we'll see to help make a step forward towards greener flight?
I think you're right to say, well, there's the social side and the economics. A greener aircraft which uses less fuel at the minute is also not just good from an environmental viewpoint, but it also costs the airline less to fly. So you get this sort of what's called binge flying, where the airlines are able to fly you very cheaply around the world. So I think it's the legislation, which again is driven by the public, and the flight shaming is one initiative, which is going to force the airlines and the industry to develop aircraft which eventually do become zero emissions. There were quite stringent targets set by, for instance, the EU for 2050, but there is still quite a gap between where the 2050 target was supposed to be and actually achieving zero emissions. It's been really impressive how, despite all the COVID crisis, where industry around the world are putting a lot of effort into this, the whole idea of trying to aim for zero emissions, rather than just tweaking the engines and perhaps putting different winglets on the end of the aircraft. But things take, it's not going to be an overnight thing, as I say. And also we've got to bear in mind the certification. We can't just suddenly radically change things and start flying. The aircraft industry has an incredibly good safety record, and that's because of taking a conservative, safety first approach. So it will come, and it's going to come quick, perhaps not quick enough for everybody. Whether that's going to stop people wanting to fly, I don't know. I'm interested to hear what Valeska and Mahdi think.
Yeah, so maybe Mahdi, could we come to you, and then Valeska, if we can come to you last, and then we'll pick up some of the hydrogen questions, you know, at the same time, if that's okay. Mahdi.
Sure, thanks. I think Jonathan's answer basically gave a proper description of the problem right now. I think certification, again, is a key issue here, especially in for technologies around urban air mobility. There is currently the 2050 thing that Jonathan mentioned is mainly around standard aviation. Doesn't really cover urban air mobility or things like that. So it is important to properly understand the implications of the new technologies in terms of certification. For my area, noise, I can say that our knowledge of new configuration is basically non-existent, leave alone the certification. So we have a long way to go to properly understand the noise and try to reduce it, and also try to make sure that they can be certified.
Can I jump back in, Richard, if I may? You did mention Norway and France in your introduction. So Norway doesn't want to have any internal flights that are creating any emissions from 2040. France, I think, is having a similar target, but is very much looking at any flight that could be done in less than 2 hours in a train. You ought to use the train, but then that means from the whole social side, you've got to get the infrastructure together. You know, we want to fly from Bristol Airport, which is nice and convenient to us, and we don't, you know, burn of fuel to go to a Heathrow, but we've got to take a bus or a car primarily to get out to Bristol Airport. So joining things up would make life a lot easier.
Absolutely. I think that's a great segue into Valeska, who maybe we can focus specifically on the hydrogen aspects and some of the questions, Valeska, that are in the Q&A.
Oh, yeah. Sure. Yeah, whichever questions you want me to answer first, I'm happy to have a go.
Well, no, if you answer the generically, and then we'll head on and pick up some of these specific hydrogen ones.
Okay. Yeah.
After that.
Yeah. So just to follow on from what you were saying about the social, economical, and technological changes, I think something that encompasses all of those ideas is this change in perspective, in terms of, you know, for the last however long, aircraft have always been based on one technology, burning kerosene and combustion, and like moving towards a diversity of different fuel sources. So looking at hydrogen, electrification, as well as combustion. I think that switch in perspective will be really useful for trying to find solutions that, so it's not just a one size fits all, looking at different solutions for different flying needs.
So picking up a couple of the questions from the participants, they tend to focus around when are we likely to see a hydrogen powered aircraft. There's a question around hydrogen has been around for a while, but we don't yet see it. So I suppose the question is around when are we likely to, and what are the critical barriers that need to be overcome, you know, in order to get there?
Well, I guess the simple answer to the when are we going to see hydrogen coming through is hopefully in the next 10 years. There'll be, well, there are already small scale hydrogen demonstrators being flown. But I saw that that someone in the chat had a really good question saying they've seen hydrogen being touted for the last 10 years, but they haven't seen much progress. And that's because the biggest challenge is because going to a new fuel source, you need the whole infrastructure behind the fuel. So you need the generation, the storage, as well as redesigning the aircraft in this case. And so until there was enough of a drive to swap over to a new fuel, it's a chicken and egg scenario where you either have the new aircraft but no way of refueling it, or you have the refueling without having enough demand for the aircraft. And so the thing that's changed in recent times is that there's been a lot of a lot of push towards a low carbon fuel like hydrogen, and there's been a lot of industry and government investment. So in Germany and France and Norway, billions of pounds towards developing the infrastructure so that we can now build hydrogen-based aircraft in the knowledge that the infrastructure for the refueling will be there when we need it. So I think that that's something that's changed recently, but because of these issues with the certification, we're rapidly moving towards being able to use hydrogen fuel cell based aviation. It's just a matter of making sure that the designs are, because they're radically new designs, so making sure that they're safe and efficient is one of the barriers at the moment. But it's one that people are putting a lot of effort into.
And maybe just a final question on, or a couple of questions on hydrogen, and then we'll move to some other topics. There are quite a lot of questions about the behaviour of hydrogen, at altitude, the understanding of that, also the impact of the water vapour release at altitude. Could you comment on any of that work?
Yeah, absolutely. So the thing with the burning of hydrogen releasing water vapor at altitude, so that's more of an issue with combustion than it is with hydrogen fuel cells. So if you're looking at a fuel cell system, then you'll be able to recapture or to mitigate that water vapor release and to reduce the contrails associated. But in terms of industry looking at research to lower the water vapor emissions, a lot of that research is being done in terms of air traffic control. So looking at flight paths, looking at changing altitudes. And there's research to suggest that may have a larger effect on the water vapor contrails than if you have that in conjunction with use of the fuel cell, then that could be the solution to the problem. And it's a nice easy solution in theory. Yeah, there are a few other technical questions I can see in the chat, but I can answer those like online if you want to go to a different topic, Rich.
Yeah, but why don't we pick up something else? There's a question here. Do you think taking the pilot off the aircraft is significant? I think this is interesting. There was a lot of talk a while ago about autonomy, and perhaps Jonathan, you might like to give us your views on where you see autonomy and pilotless flight, particularly with regard to large commercial flight, but also urban air mobility, and what do you see the barriers and opportunities there?
Well, before we get to pilotless flight, I think there's a big move to try to go from 2 pilots down to 1. But again, we've seen some of the problems that people have had with driverless cars, where eventually something's going to happen, and no matter how good your systems are, there will be a problem. And of course, the trouble is when you're flying, that makes the magnitude of something going wrong much worse. I've been on planes where they said, "Is there a doctor on board?" I don't really want to be on the plane where they say, "Is there a pilot on board?" I think we're a way off it yet. And again, with the automated flying, say over London, of urban air mobility, sort of Amazon deliveries, Uber taxis. But it's the regulation, it's the insurance that is going to stop that happening, or certainly you may say, okay, you can fly up and down the Thames. I think we're a long way off being able to build automated systems which are, I don't know, we talk about 10 to the -9, don't we, in aerospace, which I think is you drive down the outside lane of the motorway at 80 miles an hour, 1 in 10 to the 6 is you having a blowout. 1 in 10 to the 9, I think, is driving down the east coast of America and having a tree or a lamppost fall over and hit you just as you're driving along. So very small chances, but I don't think we're ready yet, or we can demonstrate that things are safe enough. I don't think Mahdi agrees.
Yeah, not my expertise quite, but I can see, as you mentioned, with other technologies like automotive, it is still something that most local governments are not happy with the certification. So I can't see how that can happen quickly with the aviation. There are lots of factors in terms of control, security, etc., that makes it very difficult to pass it through certification anytime soon. But well, never say never. You never know how.
No. And there's the cost. The cost implication for an airline to have the more crew you have, it adds up a lot in terms of the cost of a flight. I don't know.
So I think there are a number of questions relating to the fact that this is a multifaceted, multi-system level problem. And it would be good to hear from you about what Bristol is doing both internally to address that, across the different discipline specialisms, but also externally and the role that Bristol has to play. So perhaps Jonathan first, and then I'll hand over to Valeska and Mahdi.
Okay, so I showed the bubble plot, which shows lots of these individual bits of expertise, some of whom work together closer than the others. We have a big activity at the minute in the faculty where we are trying to put together this as a brand of Bristol, and whether that is green aviation or green transport. But I'm convinced that this is something that we must work on in terms of research. It's part of our remit as being an engineer that we help tackle some of the big societal problems. I'm sure it's the sort of thing that is going to attract a lot of our undergraduates if they see us working on these things. There are other universities who have big operations working in these areas together. How we tackle that on a larger basis? Well, I guess it's getting the inertia and persuading the EPSRCs, the funders, to put more money into research in this area rather than small elements. There's a lot of basic research that still needs to be done. It's not sort of like a higher TRL where we just join all these bits together. The joining them together is quite hard. But I think we need to do more in this space, but we are starting to do so. Is the headline answer. Valeska?
Sorry, Mahdi, do you want to go first? I was just typing a response. No? Okay. So looking at how we influence policymakers in terms of different technologies, I think one of the key ways that we can do this is to emphasize the additional investment that and the changes in public behavior that have to be driven by policy. And so speaking to policymakers, but also the general public, to let them know what sort of developments have been made and the advantages over existing technologies is one way that we can influence behavior and it also influence policies which would hopefully make the economics of different solutions more favorable. That would be my suggestion.
Thank you, Mahdi.
Yep, further to what Jonathan mentioned, Bristol is a member of UK ARC, which is a new consortium to tackle future activities, and also part of Vertical Lift Network, which is again another consortium to deal with helicopter before and now going into the urban air mobility activities. So we are well placed and we have very strong collaborations within the university. I can just give you an example. I think 5-6 years ago, I couldn't see myself collaborating with Jonathan because our field being so separated from each other, aeronautics and aeroacoustics. But now we have a European project on high aspect ratio wings where noise and aeroelasticity have to be tackled together. Again, I work within the university with some of my low order modeling CFD colleagues, which again, in the past was almost impossible given how far apart our topics are. But now we collaborate on propeller noise prediction and reduction. Internally, again, Phil Mellor couldn't make it today, but on the electrification and electric motors, integration is becoming key. So I cannot tackle the noise and vibration issue without knowing and understanding the electric motor. So again, we work with colleagues in Bristol on electric motors, and also in other places, Nottingham and other places, on integration as a whole. So and moving on to the policy making, it is true, we as a research institution, together with our colleagues, UK ARC, VLN, we need to work closely with the government, with BASE, with ATI, to come up with a holistic approach towards this new topic, new era of aviation. And I have to say, we are falling a bit behind compared to what's going on in the US and in the EU. There's a lot of activities going on in France and Germany. We haven't completely lost it, but we need to have a holistic approach in the country to tackle major issues.
Thank you, Mahdi. So maybe for the penultimate question, I think I'll pick up on the one that Mick has just asked in the Q&A, which I think is quite an interesting dilemma, which is by putting targets for achieving net or absolute zero, will that lead to the implementation of technologies that are advanced now, rather than taking the time to investigate, perhaps the more radical, more transformational options? So Jonathan, perhaps come to you first, then the rest of the panel.
That's a very good question. And again, if people have a crystal ball, you might know the answer. But again, there is not an infinite amount of funding, and so people are always trying to pick winners, and quite often you do pick those that are more developed. I personally think, I hope not. But then it's the design, and it's not just developing the technology, but saying, how does this apply, say, to a hydrogen powered high aspect ratio wing, which needs a totally different configuration? It's a very, it's a difficult thing to do. We're in 2021, so less than 30 years to be in 2050. Normally you'd say 7 or 8 years for a cycle of at least an aircraft, and you'd hope to go through 2 or 3, because you're not going to get it right first time. I hope not, but I fear that may well be the case. We've got to get away from let's start with the aircraft we have already and then put hydrogen in it or whatever else. I think we have to step back a bit more. I wish I knew the answer.
Thank you, Jonathan. Valeska?
I have to admit, I'm no good at multitasking, so I've been typing questions. So your question was around the need for transformative.
The deadline of 2050 going to restrict the ambition and the transformational nature of the solutions that are implemented?
I think it could be a driver, because so we have a line in the sand now where we have to reach net zero, and so there isn't this feeling that we can just make incremental changes. So as Jonathan said, like this is the time where we can have transformative new designs, and I think that it in a way it opens people up to thinking about creative solutions and getting them flying. But I think the best thing that we can do is to try and demonstrate some of these technologies, and I think that having the deadline could accelerate development. It's better than not having a deadline, right?
Thank you, Mahdi.
In my acoustics or aeroacoustics unit, I have a chart showing that we used to have a 2020 target, then 2030 and 2050, and with 2020 we didn't get there. We missed the target. But I think the only positive thing we can take is from that's our motive now. So 2030 and 2050 is really our motivation. But what really begs for is proper research into fundamentals. The incremental things that have been happening, we know that it's not going to get there. So there is a need for a proper breakthrough, whether it's coming from complete change of configuration or new technologies. it requires proper understanding, and that begs for research fund to go into fundamental research in noise or any other areas.
I mean, it's really a great time to be a graduate or an undergraduate at the minute, because the new technologies that are being developed, I think there's over 250 companies around the world developing urban air mobility solutions. The major aircraft manufacturers are coming up with new designs almost monthly.
In fact, I've got a slide that I'm just mindful of time. I can show you this a slide which my group has put together. Gives you the landscape of design out there for urban air mobility, going to sort of mid-range and mid-sized aircraft all the way to future commercial transport. So these are viable designs that major industry organizations are considering, whether it's Airbus, DLR, NASA. And you can see the design thing has exploded. There are lots of configuration and lots of new problems out there to be explored. If the tube and wing was difficult enough, this is really difficult for the next 20, 30 years.
But it's what we do as engineers. It's what drives us. Have we flown on Mars yet? I haven't seen the news this morning, but that's.
I think we're successful. That's what they said.
So it's great to see that we're not just tweaking the tube and wing. No, really interesting times. But how we do that in one, get to the right solution, if there is a one solution, I don't know. But that's why I'm an engineer. I did the maths degree originally, and then decided engineering was more exciting, shall I say? Sorry, mathematicians who might be listening.
Well, I think on that last question, I think it really just summarizes both the opportunity, the interest, and just the pace of development that's going to happen in this area over the next few years, and certainly will be incredibly exciting to be part of that. So I'd just like to draw this to a close now. Thank the panelists for their presentations and their contributions during the discussion. Thank all the participants for your Q&A. We'll endeavour to get back to the questions to you. And if you're interested to hear more about what you've heard today, then please be in touch with the university. The Industrial Liaison Office is here to help make those contacts. So please keep in touch, and thanks to everybody for their time this afternoon.
Thank you all.
Thank you.
Thanks for all the great questions. It's going to take a while to get through them.